Right, we are looking at mechanics today, and the study of mechanics focuses on forces, and we are obviously looking at forces today. Now, forces Fp of 500 newtons, of Q of 200 newtons, and Fr of 300 newtons act at point O. Find the resultant force there. Okay, we're interested in finding the resultant force in this case, and let us look at how we can actually find the resultant force in a situation like this. Okay, now how do we find the resultant force? We look at this and begin to analyze this in a very particular and very, very concise manner. So we proceed as follows. So what do we look at now? And we look at the solution to this. Okay. What are the forces here? Right, for us to find the resultant force, we need to find a combination of all the forces in the x direction and all forces in the y direction. So the forces in the x direction. So we find the resultant force in the x direction. So now looking at this, we can see that there's P with a particular angle relative to the y-axis. It's actually clearly 10 degrees, but relative to this positive x-axis, it is 80 degrees. Okay, and now we then say that Fx is therefore the force Fp times the cosine of 80 degrees plus the force Fq times the cosine of 30 degrees plus the force Fr times the cosine of 60 degrees. Okay, what is force Fp? Right, because now, okay, force Fp, looking at it very carefully, here is force Fp, but the angle here with the x-axis is 80 degrees, so that 80 plus 10 is 90, and we have the 90 degree angle there, okay? Now, the force Fq, the angle here is 30 degrees, and the force Fr, as it sits there, is actually making an angle of 60 degrees there, but 60 degrees in the negative direction. So we shall then continue to then say that what we have here, it is 500. It's 500 cosine 80 degrees plus 200 cosine 30 degrees. Now force Fr is in this direction, so you can even obviously indicate that obviously it's going to be a negative. It is negative 300 cosine 60 degrees. And we proceed to use calculators to find the resultant force of all the forces in the x direction. Right, so now if you look at this very carefully, what we have is in the x direction, this is going to be 110.03 newtons. Okay, so this will be the vector sum of all the forces in the x direction. Okay, now we continue to solve these particular problems here. And we proceed as follows. Right. Next, we find the vector sum of all the forces in the y direction. So that's going to be Fy, which is Fp in the y direction. Now, what do we have? Okay, let's analyze that. For the force P, we've already seen that the angle is 80 degrees here, so that 80 plus 10 is 90 degrees there. So now we are looking at what happens if we look at the vertical component of this force here of 500 newtons. So now we have the 500 newtons. Right, so we have that, but it is associated with the sine of 80 degrees. Let's look at force Q. Now, force Q is this one. It makes an angle of 30 degrees relative to the horizontal, and the vertical component will therefore be FQ, the sine of 30 degrees. So that is what it's going to be. So it's going to exactly be FQ, the sine of 30 degrees. Okay. Then we go on to say if we have another force Fr, the sine of 60 degrees. So you have Fy. The Fp, we saw that force Fp is 500 newtons times the sine of 80 degrees. Force Fq is exactly 200 newtons times the sine of 30 degrees. Force Fr is on the negative side. Force Fr is this side. This side is negative. But also the vertical component is also negative. So negative 300. Negative 300. Okay, but yeah, negative 300, the sine of 60 degrees. Fy. So this is 332.60 newtons. Okay. If you use a calculator here to find the vector sum of everything. Now with this said, hence, the resultant force is 1110.03. Squared plus 332.60 squared. Okay. And now we find this one here. Fr, resultant force. Okay, the resultant force, then you have 350.33 newtons. So the resultant force, we use this formula. Okay, so we can include a step here. Let us include one more step. Right, so the step is that you have fx squared plus fy squared. 1110.03 squared plus 332.60 squared. Okay, so that if you use a calculator to find the square root, we're able to see that the resultant force is going to be 350.33 newtons. Okay, if the resultant force is that, what is the angle required? Then now we note that the angle is found by using the tangent of theta, which is always fy, fx, opposite over adjacent. And we're able to see, therefore, that the tangent of theta is fy, and fy, which is 332.60 divided by fx, which is 110.03. Okay, we can put the newtons here because the numerator is a force, and also the denominator is also a force. Hence, we're able to see, therefore, that theta is arctan of 332.60 newtons divided by 110.03 newtons. Okay, use a calculator. And what we're then getting is that this is actually equal to 71.69 degrees. Or you can say it is approximately 71.7 degrees. So we have this exactly. So, and this is the result. Right, so we had to do this question, and we had to find the resultant force, and we have since found the resultant force here accordingly. And so we continue. We continue to solve these particular questions in a step-by-step fashion. And now we move on to the next question, and we try to analyze these questions together. And so it's very, very important that we concentrate and we give these maximum attention. Okay, so we're good. We're good, as a matter of fact. Okay, next question. Right, so next question. So we proceed as follows. Right, there are a couple of things that we need to consider. Let's look at the next question. Let's look at the next question. The next question is as follows. Okay, let's continue and solve the next problem. And the next problem is as follows. It is as follows. Right, in the next case, we are looking at, okay, sorry. Right, so let's continue. This is another question. We're going to call it question 2. Right, as part of question 2, we're dealing with a constant force. We are dealing with a constant force. Right, and dealing with a constant force, the couple of things that we need to consider. Okay. Now, a constant force F pulls a 50 kilogram block at a constant speed over a rough horizontal surface. Horizontal surface AB, as shown in the diagram below. The coefficient of kinetic friction the coefficient of kinetic friction, mu subscript k, between the block and the surface is 0.4. And what we have here, we have our block here. There is a force F, and this force F is at an angle of 20 degrees. Okay. We continue. So this one here is 50 kilograms. And there is a surface like so, but this surface is sort of rough. It's a rough surface. This is A and this is B. And the first question is that in 2.1, draw a labeled free body. Free body diagram showing, okay, all the forces acting on the block. 2.2, we proceed to state Newton first law of motion in words. We present now a solution to this, or sort of solutions. And we are looking at the first part. Right, a constant force F, you can underline this. A constant force F pulls a 50 kg block at a constant speed of a rough horizontal surface AB as shown in the diagram below. Okay, we saw that, but now it is at a constant speed, constant speed. And now, obviously, when the speed is constant, it means the forces are in equilibrium, and we're going to analyze what that means. As shown in the diagram below, the coefficient of kinetic friction, mu sub k, between the block and the surface is 0.4. So we have this. You need to draw a labeled free body diagram showing all the forces acting on the block. Let's analyze this question here and see what this means. Right, so if we actually have this particular setup and want to draw a labeled free body diagram showing all the forces acting on the block, 2.1. So we have the free body diagram. In the reverse direction is the kinetic friction. Straight up is the normal force. Straight down is the weight. If you do not call it the weight, we call it the gravitational force. At an angle here, there is an applied force, if you look at this very carefully, because somebody is pulling the block towards the right at an angle of 20 degrees to the horizontal. And what this means is we are having a force F. Okay, right. So we have that. Now, with that said, then, we are done with this, and this is the force diagram that is required. The next question is 2.2. State Newton's first law of motion in words. Okay, let's look at the answer to 2.2. Right, the answer to 2.2 is Newton's first law of motion. Right, Newton's first law of motion. And here is the statement. The law says a body will remain in its state of rest or motion at constant velocity unless a non-zero resultant or net force acts on it. Okay, here's Newton's first law of motion. A body will remain in its state of rest or motion at constant velocity unless a non-zero resultant or net force acts on it. Newton's first law of motion, we state the law one more time because you need to learn this. It's examinable. A body will remain in its state of rest or motion at constant velocity unless a non-zero resultant or net force acts on it. Next question. Let's do some calculations. So we're going to do calculations, and here comes the calculation. It says calculate the magnitude of the force F 2.4 normal force 2.5 frictional force. Okay, let us do calculations here. So let's look at the solutions to this. Now we want to find and calculate the magnitude of the force F. We want the size of this force. What is the size of this force? Right, to find the size of this force, there are a couple of ways to do this. So to find the size of this force, because this is an applied force, it is the applied force in this case, and therefore to find the size of the applied force, I'm sure you're able to see the force there, Tando, correct? And we are attempting to solve this particular problem, but we want to find the size of the force. And it's very important for us to be in a position to find the size of the force. So, how do we then find the size of the force? Okay. Continue. Right. to find the size of the applied force, we use Newton's second law of motion. What is Newton's second law of motion? So we're dealing with 2.3. Dealing with 2.3. 2.3 says the net force is mass times the acceleration. And so if you look at the fact that this is the applied force F, and we have here with us the weight that is straight down, the friction, and the normal force. So this one is straight down, it is the weight, and this one is the friction, and this one is the normal force. Okay, you can call it F sub n to show that it is the normal force. Okay. So that in the end, then this one here is at an angle of 20 degrees to the horizontal. That is the applied force. And so the net force now would have to be the in the direction of the motion, but also along the plane of motion. Okay, shall discuss what that means. So at this point, then it means F. It therefore means that F20, F cosine 20. Right, so because this is moving on the horizontal, so we can consider F cosine 20 degrees, which is in the horizontal, minus F sub k, which equals, because it is moving at constant speed, it means the acceleration is naught. So you can put that the acceleration is naught. And if the acceleration is naught, you come back. It is 50 kilograms. 50 kilograms of mass. So 50 kilograms of mass, and then the acceleration there. So now we continue. F cosine 20 minus, okay, this mu k is the same as the F sub k is the kinetic friction force, and therefore it is mu k times the normal force, and it is equal to 0. Okay, let us continue. What is cosine 20? Cosine 20 is 0.94 there, F minus this mu k is the same as what? This mu k is 0.4. It's 0.4 into. Right. What is the normal force? Let us find the normal force. Let's find the normal force on the side. What is the normal force here? The normal force of this situation, let me find it in yellow to make sure that we create a wonderful contrast in the colors. Because the normal force has to do with the vertical. And we understand, therefore, that when it comes to the forces in the vertical, we're going to find F net, which is MA. Right, finding F net, which is MA, we consider every force that is what? That is in the vertical. So we're going to consider the couple of those forces. And one of those forces there. Okay, we can consider, for instance, the weight. Fg or W. And then now the weight is straight down, but we can see that the normal force is up. And also the F sine theta, okay, you can call this one Fx, call this one Fy, okay, it's easier like that. So that you come here and you put here Fy, which is 0, okay, because it's not accelerating upwards, okay? This object is not accelerating upwards, so it means the forces in the vertical themselves sort of balance up, and we're able to see that the forces there tend to balance up, okay? So that is something that is extremely important for us. Okay, so we continue. We continue. Right. Right. So, which means therefore the force of gravity, the gravitational force, is the same as Fn plus Fy. So we continue. Right. So as if it's my phone, it doesn't have space or okay. Right, so that is Fg there. So let's find this. So what is this and what do we do here? So we can find the normal force, which means therefore the normal force is Fg minus Fy. Okay, so you come here, in the place of this, you put the normal force, which is Fg minus Fy, and this is equal to 0. So which is 0.94 F minus 0.4. This normal force, which is the force of gravity, which is mg minus the vertical component, which is actually F, the trigonometric sine of 20 degrees, and this is equal to 0. So now what we're getting here is the following. So we proceed to solve these particular problems, but we solve it step by step as follows. As we continue with our focus on 2.3, I want us to solve more problems that, and to first and foremost finish this particular one. So, which means that we have 0.94 F, 0.94 F minus 0.4 mg minus F sine 20, which is 0. Right. Okay. We want to find the force F, so this is 0.94. 0.4. What is the mass? The mass is 50 kilograms into 9.8 meters per second squared minus F sine 20, which is 94 minus, okay, so you have 0.4 into 50, 9.8, and then negative by negative is plus 0.4, F sine 20, which equals 0. F and F here. So we want to solve for F. So to solve for F, you move this ones to the other side. 0.4, 50, 9.8. So transpose it is 2. And then now here would have taken a common factor. Okay, if you take a common factor out of these two, you'd have 0.94 plus 0.4 times sine 20. Oops, sine 20. Which means 2.3. Okay, which is 0.450, 0.450, and then 9.8. Okay, divide by 0.94. 0.94 into 0.4 sine 20. So now we have this 0.4 0.4 times 50 times 9.8 divided by 0.94 plus 0.4 times the sine of 20. See what we're getting here? Okay, here it is then 182.01 944 newtons. Approximately this. And now this can be rounded off. Okay, so it is about the force that is required there. And it is the applied force. Right, and we have solved the applied force question, and here we are. But now, obviously, if you look at these carefully, we're looking at this situation, and given this situation, we had to look at this and be in a position to perform the calculation and calculate the magnitude of the force F. Then in 2.4, we want the magnitude of the normal force. 2.4, the normal force. Right, so in 2.4, we are interested in the normal force. And the normal force, let us look at what is happening here. We have the free body diagram that shows the force of gravity. We have this one, which is the force of kinetic friction, the applied force. And it acts at an angle of 20 degrees to the horizontal, the applied force. And we have the normal force straight up, perpendicular to the ground. Okay, or perpendicular to the surface. And therefore, to find the normal force here, we proceed as follows. We proceed as follows. Right, so we then say F net by Newton's second law is mass times acceleration, but obviously because there is no vertical motion of this object, we need to also include all forces in the vertical. So let us include all forces in the vertical. So now the forces in the vertical are as follows. So there is force of gravity that is straight down. Okay, and then there's this upward force, which is the normal. And there is also this upward force that is the Fy, F sub y. And then it is the mass times the vertical acceleration, which is 0 because there's no motion up. And as a consequence, what this means is therefore that the force of gravity is mass times acceleration. And this F normal is what we want. The upward, the vertical component of the applied force is actually F, the sine of 20 degrees, which equals 0. Okay. So the normal force, therefore, is mg minus F, the sine of 20 degrees. The normal force now is the mass. What is the mass? 50 kilograms. 9.8 meters per second squared minus the applied force. Okay, can you do something here and say this sine 20? Sine 20 is about 0.34 F. Okay, now multiplying these things, we're going to have the following. So we have F normal, 2.4, which is F normal is equal to 490 minus 0.34 F. 490. 0.34. Okay, so we have this force here we have just got, which is 182.01 944. 182.01 944. Okay. And then now what do we get here? Which means the normal force now is what we get here. Using a calculator, let's just use a calculator and see what we're getting. Okay, let's use a calculator. 490 minus 0.34. Okay. Now I'm just using the calculator here, which is 490 minus 0.34 times 182.01944. Okay, so this one is 428.11. 33904 newtons. Okay, it's approximately this. Okay, this is just an estimate answer. Just note these. Right, so we have exactly this answer. So to a couple of decimal places, F normal is approximately 428.11 newtons. Okay. Right now, let's look at 3.4, 2.5. Let's see now. 2.5, we need now the frictional force. Let's calculate the frictional force. So 2.5. Let's calculate the frictional force, which is F sub K, which is mu K times the normal force. Or you can write this mu sub K, which is the normal force. Right, F sub K, therefore, is what is the normal force? What is the coefficient of kinetic friction? Is 0.4. The normal force is about 428.11. 0.11 newtons. Okay. F sub K, 171.23 newtons. So that is what we have. Okay, but we need to just check this one, please. Let's use a calculator here. Calculator to verify this. So you have 0.4 times 428.11. Okay, 171.244 approximately. So yeah, this is just, these are estimate answers. Right, 0.244 newtons, meaning the force of friction is approximately 24 newtons. 0.24 newtons, and therefore it is the frictional force. We've got the frictional force now. And the frictional force is this one here. Okay, now we're going to look at the next question. To look at the next question. Right, so in looking at the next question, we obtain the following. Okay, let's look at this one, part 2.6. Part 2.6. This is 2.5, then let's look at 2.6. Right, in 2.6, you must be able to give a reason Give a reason why the block will move slower than before. Solution? Right, so let's look at the solution to 2.6 right now. Give a reason why the block will move slower than before. Okay, I need to put a situation here. I need to put more information here before this question. So let me load another part of the question, an extension part. The same constant force F is now applied to the block. Over the same rough horizontal surface. As before, but in the direction shown below. Okay, so we continue. So we continue. We continue. Right, in continuing, the couple of things we shall look at here. And we have the following. Right, so there's a direction that we need to show here. We have the block. Which is 50 kilogram or 50 kilograms. And we have here friction, a force, 20 degrees. Right. Okay, we'll continue. We continue. So now this is A, and that is B. That is A, and that is B. Give a reason Give a reason why the block will move slower than before. Okay. Give a reason why the block will move slower than before. Okay, we look at the solution to this. $2.6. Right, so the same constant force F is now applied to the block over the same rough horizontal surface as before, but in the direction shown. So here's the force that is the same, but now it's applied at this particular angle. It's no longer a pulling force, but it's sort of a pushing force now. And now we are then saying, if this, because before it was a pulling force, looking at this force diagram, but also it was clearly a pulling force in this case. What happens now if we push the block? We just push it. We push it. So, okay, let's see now. If you push the block, what happens if you push the block? Right, you push it. And we are then saying, if the pushing happens, give a reason why the block will move slower than before. We're arguing that the block is not going to be faster, but is going to be slower when it is being pushed than when the block is being pulled. And now we are saying, give a reason why that is the case. And here is the reason. The reason is that the normal force increases. Hence, the frictional force increases. Making it harder to move the object forward. Okay, let's analyze these carefully together. The normal force increases, hence the frictional force increases, making it harder to move the object forward. Okay, so that is the reason. The normal force increases, hence the frictional force increases, making it harder to move the object forward. Next question. That is the reason why the block will move slower than before when you push it than when you pull it. When you push it at an angle and versus when you pull it at an angle. Okay, so let us look at more problems now. Let's look at more and more problems. Right, let's look at question 3. Right, in the diagram below, a 2 kilogram block is connected. It's connected to a 1 kilogram block. One kilogram block by means of a light inextensible string. The blocks right, the blocks are pulled up an inclined plane which forms an angle of 28 degrees to the horizontal. The sides of the blocks which touch the inclined plane have the same area. Right, so at this point, if we look at this situation, this angle is 28 degrees. There's a block of 2 kilograms. It's connected to another one of 1 kilogram. And there's this force here that is 30 Newton force. The kinetic frictional force between the 1 kilogram block and the inclined plane is 4 newtons, while the kinetic frictional force between the 2 kilogram block between the 2 kilogram block and the inclined plane is 8 newtons. Okay, this is question 3. So right here, 3.1, you need to draw a labeled free body diagram showing all the forces acting on the 1 kg block. Okay, so let us look at this question. Let us answer this particular question. As we answer that question, I want us to also prepare to answer this particular question that says that we need to be able to state Newton's second law of motion in words. Solution. Perhaps before present a solution to that, let's look at another question. This next question is as follows. Calculate right calculate the magnitude of the tension in the string connecting the blocks. Okay. Now we're looking at this particular question here. Right, looking at this particular question, the couple of things you need to consider. Let us try to analyze these and see what we can do, because we're saying in the diagram below, a 2 kilogram block is connected to a 1 kilogram block. By means of a light and extensible string, the blocks are pulled up an inclined plane, which forms an angle of 28 degrees to the horizontal. So we have these two blocks connected to each other, and they are pulled up by a force of 30 newtons, and the angle here is exactly 28 degrees. The sides of the blocks which touch the inclined plane have the same area. Okay, the sides of the blocks which touch the inclined plane have the same surface area. Okay, interesting. Now let us solve this particular question here. And in the first part, then we have the setup as shown below. Okay, we continue. The kinetic frictional force between the 1 kg block and the inclined plane is 4 newtons. While the kinetic frictional force between the 2 kg, so between the 1 kg and the inclined plane is 4 newtons, while the kinetic frictional force between the 2 kg heavier block is 8 newtons. Okay, so note that draw a labeled free body diagram showing all the forces acting on the 1 kilogram block. Okay, let's draw a labeled free body diagram. Right, in drawing the labeled free body diagram, we look at 3.1. Right, so we have here the weight that is straight down. Okay, don't want to call it the weight, to call it the force of gravity. Right, so with that mentioned, we're drawing the free body diagram, showing all the forces acting on the 1 kg block. Okay, but obviously, if you look very carefully here, the 1 kg block is ahead. So it has an applied force, it has the force of friction, but there's also tension. So, which means we have here the applied force, Fa, and then we have the tension, but also we have the F, or you can call it the friction force, this one. Perpendicular to the slope is what we call the normal force. You can call it capital N or the normal force, like that. Okay, so this is the free body diagram of the 1 kg block that is ahead, the leading block, because the leading block has an applied force, the tension and friction force, the weight, and the normal. Okay, so we're happy. Next question, 3.2. State Newton's second law of motion in words. Newton's second law, state Newton's second law of motion in words. Let's state Newton's second law of motion. So we are stating here Newton's second law of motion in words. Right. When a net force is applied to an object. An object of mass m. Okay, an object of mass m it accelerates the object in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Right, Newton's second law of motion is very, very straightforward and states that when a net force is applied to an object of mass m, it accelerates the object in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. So that is right. That is Newton's second law of motion. A couple of ways to state it, but that is certainly one of the ways to state it. Okay, let's look at the next question. Okay, now the next question is this one here. We need to perform a calculation. Calculate the magnitude of the tension in the string. Okay, I want to calculate the magnitude of the tension in the string connecting the blocks. Okay, let us see what we can do. Let us see what we can do with this particular question here. Right, to calculate the magnitude of the tension in the string connecting the blocks. And so we can find the magnitude of the tension in the string connecting the blocks. And let's just do this one here with ease and celebrate. Okay, so we're looking at this one in 3.3. 3.3. You have the net force, which is MA. For the 1 kilogram block, For the 1 kilogram block, there are a couple of things you need to consider here. And we need to look at this very, very carefully. Here is the 1 kilogram block. In particular, we looked at the free body diagram here, and we're able to see that for the 1 kilogram block, the applied force is 30 newtons. So surely here we have the applied force that is actually 30 newtons. So to do this, then we proceed as follows to actually calculate the tension in the string that connects the two blocks in the diagram. Right, so we shall do the following, and we shall then say the 30 Newton force, 30 Newton force minus the tension minus, because it's on a slope, you have the parallel component, which is mg for the weight, the sine of the angle of inclination of the slope, but there's also kinetic friction in the direction opposite direction of motion, and this is the MA. Okay. Now, this therefore is 30 minus what? Let us see what we're getting here. So it's 30 minus the tension minus the mass of the 1 kilogram block. The mass is 1 kilogram. And then this one is 9.8 gravitational acceleration times the sine of 28 degrees minus the friction. The 1 kg block has a frictional force of 4 newtons, because we're told here the kinetic frictional force between the 1 kg block and the inclined plane is 4 newtons, and the kinetic frictional force between the 2 kg block and the inclined plane is 8 newtons. Okay, so we have the 4 newtons. 4 newtons for the 1 kg block, and this here is the mass times the acceleration. Okay, so, and if we look at this, therefore, we're going to proceed as follows. We have the 30 minus these minus 4, and this is actually 21 point, if you use a calculator, 21.399 minus the tension in the string, and this is equal to 1 times the acceleration is actually the acceleration. We call this equation 1. We proceed now for the 2 kg block. Still looking at part 3.3, but now for the 2 kilogram block. The 2 kilogram block is not different at all. Right, if you look at the 2 kilogram block, it's actually also, it has its weight, but it has the normal force. It has the friction, kinetic friction. It has the tension in the string. But the weight that is there will always have its own component. So we have the parallel component, and here we have the perpendicular component of the weight. Okay, with that said, then it means that we have F net, which is MA. Okay, then we have the tension minus, okay, we have the tension minus the tension is upslope, but now you have the parallel component, which is exactly mg, the sine of 28 degrees, minus fk, which is mass times acceleration. Tension minus the mass is 2 kilograms, 9.8 times the sine of 28 degrees minus the tension, rather the kinetic friction. Kinetic friction force is exactly 8 newtons of the 2 kilogram block. Okay, it was given. The mass of the 2 kilogram block is 2 kilograms times the acceleration of the system. T minus these two guys here, this and that on a calculator, they give us minus 17.201. Twice the acceleration. Object 2. And so now we have the following. So we have equation 1, equation 2. Equation 1 is actually 21.399 minus tension equals the acceleration. So we're still looking at 3.3. So for equation 1, we have 29.399 minus the tension, which equals A. Call it equation 1. Which the next one is tension. Tension minus 17.201, which equals twice A, call it equation 2. Then we proceed to say we want the tension. So if you want the tension, we can be in a position to find the tension because the question says that we need to calculate the magnitude of the tension in the string connecting the two blocks. And so we need to find the tension. So to find the tension, you can say substitute equation 1 into equation 2. Okay, so which is tension minus 17.201 equals 2 times the acceleration, which is 21.399 minus the tension. Tension minus 17.201, which equals 2 times. Okay, so we're dealing here with 2 times that. 2 times 21.399, which is actually 42.7898 minus twice the tension. Bring this one across. 3 times the tension. Right, you therefore have 3 times the tension, then you have 17.201 plus 42.798. So which means that the tension is actually 59.999. And then obviously we are finishing 3.3, and then we have 3 times the tension, which is 59.999. And then now we need the tension, and the tension is 59.999 divided by 3. So divide by 3. 59.999, you divide it by 3, and the answer is 19.99966 and so on. So, and therefore, as a consequence, then T is approximately 20 newtons. Right, so we found the tension in the string that connects the two blocks, because the two blocks are here. We can see the two blocks, but they're connected by a string, and the string is just there between the two blocks. And it is most certainly connecting the two blocks there. Okay, let us look at the next question. Let's look at the next question. The next question is as follows. Okay, the two blocks now. Right, so the two blocks, the two blocks are interchanged. Are interchanged so that the same 30 Newton force is now acting on the 2-kilogram block along the inclined plane as shown in the diagram below. In the diagram below. So we have this situation, 28 degrees of slope, 1 kilogram mass. Okay. And then now, two kilograms, 30 newtons. Okay, we have this situation. Now, because in the beginning, in the environment we had earlier, in the setup we had earlier, the 1 kilogram block was at the front. Now, we just switched, they just switched places. Now we just put above the 2 kilogram, sort of put in front the 2 kilogram block. Now we have the 1 kg block at the back of the setup. And then now we have this particular question. Okay, so this was like 3.3, and this one is going to be 3.4. try in 3.4. How will the acceleration of the system change write down only increase, decrease, or remain the same? Or remain the same? So then now we have 3.5 as well. How will the tension in the string connecting the two blocks change? Write down only increase, decrease, or remain the same? Okay, let's look at this. Present the solutions to this. Right, so presenting the solutions to this, a couple of things we need to consider. So the two blocks are interchanged so that the same 30 Newton force is now acting on the 2 kg block along the inclined plane as shown in the diagram below. So the 30 Newton force is actually there. How will the acceleration of the system change? Write down only increase, decrease, or remain the same. How will the acceleration of the system change in this case? Let us analyze this particular question. How will the acceleration of the system change? Write down only increase, decrease, or remain the same. Because it is the same force that is applied to the system, we understand that in the part 3.4, remains the same. Remains the same. 3.5. How will the tension in the string connecting the two blocks change? Write down only increase, decrease, or remain the same. So how will the tension change now? Because we had the 1 kg block in front and the 2 kg block was here at the back. Now we interchange. How will the tension here change? Okay. So we can see that now this tension will be caused by the 1 kg block that's now pulling backwards, so that, and the 1 kg block is smaller in mass than the 2 kg block and is lighter. Okay. It's not so heavy because in the beginning we had 2 kg here, now we're having 1 kg. So it means that the force in the string is now smaller. The weight is smaller. The mass is smaller. Okay, we are excited to say, surely putting a smaller block of 1 kg instead of the 2 kg in the back will lead to a decrease in the tension in the string. It's a decrease. So it decreases. It decreases. Okay, it decreases. Okay, right. So that was 3.4, 3.5. Okay, let's look at another scenario. Let's look at another scenario. In this scenario, we have the following. Call this question 4. In the diagram, below, a 1 kilogram block or 1 kilogram mass and a 2 kilogram mass are connected. Okay, they're connected by an inextensible string of negligible mass. The string is passed over a light frictionless pulley. So that the masses hang down as shown. Initially, the system is held stationary Okay, let's analyze the system. I want us to look at this system, and here is the system. And it is a system of blocks. Like so. And this is like that. Continue. We continue. Right. So you have this one here. And you have the 1 kg. Like so. Two kg. Okay. That is question 4. Then we are looking at 4.1. In 4.1, you need to draw a labeled free body diagram. Showing all the forces acting on the 2 kg block on the 2 kg mass. 4.2, calculate the time it will take the 1 kg mass to move a distance of 1 meter. Of 1 meter when the system is released. Released. Okay. Let us proceed to solve these two questions. Look at the solutions to this now. Part 1, 4.1. Yes. Draw a labeled free body diagram showing all the forces acting on the 2 kg mass. Draw a label free body diagram showing all the forces acting on the 2 kilogram mass. Let's look at that. And obviously the 2 kilogram mass is here. So this is sort of a pulley system. So you have sort of a system like that. So now we continue to solve this problem in a step-by-step fashion. Okay, if you look at these 2 kilogram, how many forces are acting on it? Okay, we have the force in the tension upwards, and the weight, looking at the 2 kilogram block. So now in 4.1, you have the weight or the gravitational force, and you have the tension upslope like this. Yeah, these things are not to scale. So need to be careful that this is just rough. It's a rough sketch. Rough sketch of the situation. Looking at the 2 kilogram block. Okay, here the 2 kilogram block is sitting here. But we're just showing the forces acting on it. So because it is hanging there in the air, this thing is like a system that's like hang in the air. So this one is having a weight and this one is having an upward force. An upward force. So it is the upward force is the tension and the weight is downwards. Okay. 4.2. Now you would then have to calculate the time it will take for the 1 kg. Okay, now I'm gonna illustrate something here. I'm gonna show the marks, okay, the mark allocations, because if you check very carefully in the part 4.1, the marks are 2 here, and then in part 4.2, the marks are 7. So just check this. Okay, the marks are 2 up there, and the marks are 7 at the bottom. So yeah. Okay, so just note that part. Okay. We continue to solve this problem. Now, this one is 7 marks because you have to draw a level free body diagram showing all the forces acting on the 2 kg mass, and we showed the 2 forces, the weight and the tension, okay? Now, in the second part, we need to calculate the time it will take the 1 kg mass to move a distance of 1 meter when the system is released. Calculate the time it will take for the 1 kg mass to move a distance of 1 meter. 1 meter. Okay, let's see now. When the system is released, because now it's just balanced, but when it's released, this one is going to move 1 meter. Calculate the time it will take for the 1 kg block, this one here, because when this thing is released, the system is released, we expect it to accelerate that way. So we expect the 2 kg block to accelerate downwards and the 1 kg block upward. Okay, good. Now, because this one is heavier, the 2 kg is much heavier than the 1 kg, we expect to go down and the 1 kg will be lifted up, okay? Now, this is expected because the 1 kg and the 2 kg are not of the same mass, okay? They're not of the same mass, so note this. Now, we need to perform a calculation. What is it? What is this calculation? You need to calculate the time it will take for the 1 kg mass to move a distance of 1 meter when the system is released. we look at the solution to this. Okay, what do we do now? We solve this problem in a step-by-step fashion. Right, so here is the 1 kg block. There's a weight, but also there's tension. So it means that F net is MA. For the 1 kilogram block. Okay, so here you have the 1 kilogram block. Okay. If the system is released, we expect it to go up. So the tension is going to be much stronger. Why will the tension be much stronger? Because the 2 kg is heavier, so it's going to go down, and this one is going to go up. So it is the tension minus the weight, which is MA. Tension minus 1 times 9.8, 1 times acceleration, T minus 9.8, acceleration. So let's call this one equation 1. Still going on with 4.2. But for the 2 kilogram block, here comes the 2 kilogram block. And we have this. Because it's heavier than the 1 kg, so we expect the weight to be bigger. So that you're going to have this one minus the tension. Okay, F net. Okay. F net is MA, which means W minus tension. Okay, because the weight is bigger than the tension, is going down these 2 kg and the 1 kg is going up. The weight is mg minus the tension, which is ma, which is 2 into 9.8 minus tension, which equals 2a. 2 times 9.8 is 19.6 minus tension is 2a. So this is equation 2. 4.2. Okay, so we have that T minus 9.8 is acceleration. We called this equation 1. 19.6 minus the tension equals 2a. Is equation 2. Okay. There are many things we can do. We want to find the acceleration here, so we can say here 19.6. Move the 2a to the one side and the tension and call this equation 3. Okay, you need to repeat this question during your own spare time. You need to watch the video and write down the notes. You need to have your physics book, your physics notebook, counter book, where you write everything that we're discussing. So now we can substitute 3 into 2. Right, substitute equation. Equation 3 into 1. So that in the place of the t is this. It's 19.6 minus 2a minus 9.8, which equals a. Move this one. Now, what is 19.6 minus 19.6 minus 9.8? Let's just do this one. We have 19.6 minus 9.8, which is 9.8. Still continuing with the 4.2 question. 9.8 equals 3a. Which means that 9.8 you divide by 3, which means 3a you divide by 3. And okay, if you have 9.8 divided by 3, which is exactly 3.267. You can write approximately a acceleration is approximately 3.27 meters per second squared. Okay, see, this will be the acceleration of the entire system, but in 4.2, we use the equations of motion. So one equation of motion is that delta y is vi delta t plus half a delta t squared. Okay, so the situation here is that this is going to accelerate, but we are asking the question, calculate the time, the time it will take for the 1 kg mass to move a distance of 1 meter. So we understand that this 1 kg mass, when this is released, 2 kg is bigger than 1 kg. So we expect the 2 kg to go down and the 1 kg to go up. Okay, so when that acceleration happens, we expect this, we are interested in the time it will take for the 1 kg mass to move a distance of 1 meter. 1 meter, 1 meter upwards. So it's going to move 1 meter upwards. So if we consider downward as positive, right, we're choosing downwards as positive, and therefore it's going to go up by -1 meter. It was initially addressed, and therefore you have 0 delta t, 0 initial velocity. Half into the acceleration is going to be up, and therefore it's going to be minus 3.27 delta t squared. -1 is 1/2 of minus 3.27 delta t squared. Okay, we divide here everything, which is 2 divided by 3.27 delta t squared, 4.2, which is 2 divided by 3.27, which equals 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 3.27, delta t squared. Here you apply the square root on the left and the square root on the right. Okay. Okay, now let's find the answer to this. So if you look at this now, you want to find the change in time. 2 out of 3.27. 0.78. Zero 0.78 seconds. So, okay, look at the question. The question was, calculate the time it will take for the 1 kg mass to move a distance of 1 meter when the system is released. Okay, and here's the system. When the system is released, because it is now supported and is not moving, but when the system is released, we said the 2 kg block is heavier and therefore it's going to go down and the 1 kg block is going to go up. Look, calculate the time it will take for the 1 kg mass to move a distance of 1 meter when the system is released. Okay, when it moves a distance of 1 meter, so it's negative 1 meter. The acceleration is going to be obvious because we're choosing downward is positive. Downward motion is positive, meaning the 1 meter is going to be upwards because the acceleration, the 1 kg is going to move up when the 2 kg moves down. And the acceleration is going to be upwards, and therefore the time is 0.78 seconds. And that answers the question that said, calculate the time it will take for the 1 kg mass to move a distance of 1 meter. So for the 1 kg mass to move a distance of 1 meter, it will take a time of 0.78 seconds when the system accelerates like this. 0.78 seconds. Right, I think that it's enough for today, and thank you for joining us. I'm going to contact you again during the week for more learning. But our main lesson, which is like 2-hour minimum time, is on Mondays for science. But yeah, we're going to do more during the week, or if not during the week, then during the weekend, I'm going to just find time and let you know the day before or a couple of days before, 2 or 3 days before, so that we can have more science practice. Okay. Right. Otherwise, thanks a lot, Tando. And thanks, Lerato. And I'll see you guys. Okay, thank you guys. I'm gonna pause this video. I'm gonna pause this science video so that you can watch it. When you watch science videos and math videos, please take down notes. You copy down the questions, you write down the answers, you close the answers, see if you can do the questions on your own. That is how to learn mathematics and science. Mathematics and science is not like watching a movie. You can never just watch a movie and then suddenly you are able to perform. It's like if somebody who plays somebody who plays soccer. I cannot believe that somebody can watch Dr. Kumaro playing and then believe that when they are put on the pitch, they're gonna play like him. It's not. It doesn't work like that. Normally, you need to be on the field of play. You need to practice. You need to stretch your muscles. Mathematics is not different, and science is not different. So you need to always, okay, now I've seen how it's done. Let me close the answer. Let me see if I can do it. Like that until you are perfect. You know, it's like a sport. Mathematics and science are like a sport. Otherwise, thanks a lot, guys. See you next time. Which I don't know what's up. So, but Mondays, mathematics, Mondays 8 p.m. mathematics, Fridays 8 p.m. Mondays 8 p.m. science, Fridays 8 p.m. math. The weekend 4 p.m. on Saturdays is math group discussion. Sunday 4 p.m. is also math discussion, because I'm putting a lot of the math over the weekend, because the math is very important for you to get into university. So you need to master it more, I believe. But we shall have more of the science. I can always slot in more of the science as well during the weekend. But yeah, I'll let you know. Okay, thank you guys, and goodbye, and have a good night. Okay, goodbye, guys.
Bye.
Bye.
Thank you.
Goodbye, guys.